Hi, in today's video, we'll be continuing the study of combinatorics and how we can use it to prove different identities. So let's talk about very famous and very powerful identity used in matrix computation often. This is the Vendemon's identity. And the Vendemon identity states that the summation from I to 0 to R of the product of two choices, M choose I and N choose R minus I. So if you expand out, it's M choose 0 times N minus N choose R plus all the way to M choose R times R choose 0. This expansion is just the same as M plus N choose R. So let's see why that's the case. I'll give you two proofs, but there's many other proofs. The first proof is the algebraic proof. So you can see this is the binomial coefficient for x plus 1 plus x to the power m plus n. And so on the left hand side, we already have this expression out. And when you expand out, it'll be this expression. On the right hand side now, we can think of it as breaking into m terms and n terms. And so when we expand out for the m terms, and this is the expansion for the n terms. And then we can see when we do the products and Cauchy product and everything, this will be the final expression. And then we just need to compare the x to the power r term, and we will see that m plus n choose r is the same as m0 n r plus m choose 1 n choose r minus 1 all the way to m choose r times n choose 0. And so you can see this is just the application of the binomial theorem to expand on both sides and just compare coefficients. While this is one of the simplest way, another way is to think of the combinatorics proof, but you need to think of what argument you want. And actually following the argument used in the binomial theorem or how we choose the factors, you can roughly see how we're going to do the combinatorics proof. So the second proof is using combinatorics, and we just consider the following set with m plus n elements, m of which is labeled as a to m, the other one is b to bn. And so the number of ways to choose r elements is m plus n choose r. And likewise, we just need to choose, we can choose 0 from the a side, and so that's m choose 0. Then all our r elements must come from the b side, so it's n choose r. And so, but there's another case, which is when you choose one element here and r minus one element here, and you continue all the way until you choose r elements here and 0 elements here. And so this proves Vendemon's identity. You can think of other proofs like creating the shortest path proof or everything, but basically other combinatorics proof relies on this fact. And so we'll skip those other proofs, and with these two proofs you can see how the algebra proof, while it looks more convoluted, it's a very procedural way, whereas in the combinatorics proof you need to think of the argument. And so let's use Vendemon's identity to prove some basic results before we can see a very interesting result. So let's just take a simple example. We just put m and n to be both r, and then this will be the expression. We know that r choose r minus I is the same as r choose I, and so this you can simplify, and hence by Vendemon's identity, this is just 2r choose r. And so n choose r squared from r0 to n is just 2n choose n. We shall use this for our next proof. In our next proof, we have this very complicated looking algebraic expression. And then we'll just show that it equals to 2n choose n squared. Why? This summation, we can, from r to 0 to n, we can introduce this factor of n to factorial squared. So now we divide by n factorial squared, we need to multiply by n factorial squared, and we can split the numerator and denominator originally into this. 2n factorial over n factorial squared is the same as 2n factorial over n factorial times n factorial. Or the other n factorial, you can think of it as 2n minus n factorial. So that is just 2n choose n. And for the other side, it is now n choose r squared. Since this term doesn't rely on r, you can bring it out to as it's a constant in the summation, and so the summation is now r from 0 to n of nr squared. And what we can see from earlier here is that this factorial reduces to 2n choose n, and hence we get the final expression that we want. So you might be always thinking, why are we doing all these identities? Well, in certain cases, it helps us simplify this very complicated notation into a simpler case. And in other cases, is if you have a generating function that we might cover in a future video, and its sequence is defined by this, its coefficients, then you can get a closed form for the expression over here. But you can read up more about generating functions or keep an eye for our future video, and take note that all these identities, all these algebraic identities that we prove, allows us to create and use it for other purposes, such as using it for generating functions and creating closed form expressions, which are very useful when you want to deal with computation, as this summation will take a long time to compute, whereas this value will take a very short time in the computer. So let's move on to a very interesting use of Vendemon's identity in matrix computation. Let's consider a square matrix of order k, where the nr entry is just n plus r minus 1 choose r. So let's take an example of k equals to 3. So it is like that. n plus r minus 1 choose r. So it's 1 choose 1, 2 choose 2, 3 choose 3 for the first row. For the second row is 2 choose 1, 3 choose 2, 4 choose 3. For the third row is 3 choose 1, 4 choose 2, 5 choose 3. You can expand out easily to show that this is the matrix 1 1 1, 2 3 4, 3 6 10. You can directly compute the determinant and show that it's 1. But now, we want to show, and I claim, that for a matrix A of any order, not just 3, that follows this property of the nr entry being n plus r minus 1 choose r, its determinant is always 1. Let's prove it. Let's consider two matrices. Two triangular matrix to be specific. Matrix B is where it is a triangular matrix where the elements in the diagonal is just C choose R, R choose R, and below it you just add 1 to the R, to the first, to the top row, to the top choosing identity. So it's like in the first column is 1 choose 1, the second one is 2 choose 1, and you go down the row, and you can see this is how the expression will be. For matrix C, you flip it around, and now change a bit. In our diagonal, is everything choose 0. So it's 0 choose 0, 1 choose 0, all the way to k minus 1 choose 0. And you fill up the rest accordingly. In the row now, you increase it from C choose 1, choose 1, C choose 2, choose 2, all the way to k minus 1 choose k minus 1. Second row is 1 choose 0, 2 choose 1, all the way. We can easily compute the determinants now because it's a triangular matrix and we only need to calculate the diagonal entries product. So the first one is obviously 1. The second one is also 1. because all these terms are here are 1. And for the matrix C is also exactly the same. All the terms here are 1, so the determinant is 1. Now we claim that B times C is exactly A. And why? Because the NR entry of BC is the summation of BNI times CIR. And so we run this from 1 to order K. And hence we see that the BNI entry is N choose R, where the CIR entry is R minus 1 choose R minus I. By the Vendemon's identity, you see that how this type of expression with a summation and 2 products of choosing allows us to simplify it. And so it simplifies to when M is just N and N is R minus 1. And so it's just N plus R minus 1 choose R, which is exactly what our property states. And so B times C is the same as A. I'll let you read this slide by uploading it so you can fully grasp it and see for yourself that this is actually true. And so, since A equals to B times C, determinant of A equals to determinant of B times determinant of C, which is just 1 times 1, and so determinant of A is 1. And hence, this is an interesting use of Vandermonde's identity. Thank you for listening, and I've hoped you have enjoyed this short video on Vandermonde's identity. There are many other uses of Vandermonde's identity, and I've just showed you a short introduction into it. Feel free to explore more and leave any comments down below. Thank you.